Unpacking this question, we start out with an object, this block, sliding along like this, and it collides with this other block that is attached to this spring. And the first question is just simply wants us to determine what the linear momentum and kinetic energy are. So our linear momentum in this case, P equals mv, we have a mass of 0.2, a velocity of 3, and that gives us a momentum of 0.6 kilogram, 60 kilogram meters per second. So that's the first part, pretty easy. And the second part, it's kinetic energy. 1/2 mv squared, 1/2 that 0.2 times 3 squared, and that's 1/2 of 1/5 times 9. So that's 9 divided by 10, or 0.90 joules. So A and B, parts 1 and 2 are very straightforward. Part B, the second part, wants to know what happens to their these quantities, what happens to the quantities immediately after the impact. So in physics, of course, the why things move, why they move the way they move has to do with the law of conservation of momentum and the laws of conservation of energy. And so the linear momentum immediately after the impact is going to be the same. Immediately after the impact, the momentum is 0.60 kilogram meters per second. That's because of the law of conservation of momentum. Then we could do a calculation around this. P0 equals P. We know we have 0.60 before. And afterward, the two masses stick together. So mass 1 plus mass 2 times that final velocity. The first mass was 0.2 and the second one was 1.3. Gives us a total of 1.5, 0.6. And then we get velocity is 0.40 meters per second. But the question wants the initial momentum, or the law of conservation of energy. The law of conservation of momentum, the initial is going to equal the final. So we can do a calculation back on that to find out what that velocity is. So 0.60 equals 1.5 times v. Let's just see that it equals the 0.60. So what is that momentum equal? We had 0.40, and sure enough, we get 0.60 kilogram meters per second. Now the kinetic energy is a different beast. The kinetic energy afterward is 1/2 mv squared. Now our mass is the combined mass. It's effectively one particle right now. Two particles have become one. So the mass of the two of them together is 1.5. And the velocity we determined right here was 0.40. So we have 1/2 times 3/2 times 4/10 quantity squared. And so we see we get 3/4 times 16/100, and this becomes 4, and we get 12/100. So 0.12 joules is the kinetic energy after the collision. So again, a simple calculation using the speed beforehand. The momentum, part C is a little more tricky because some different approaches are being combined here. But basically, we have a situation where we have our equilibrium position right here that occurs at the instant the 0.2 kilogram mass hits the spring. And these two then stick together, and the spring moves back and forth like so. And XO The amplitude is XO, which is the extreme position. It's going to go back and forth between these two positions, XO and minus XO, back and forth. And so if we look at what happens from a perspective of energy, there's kinetic energy, which interestingly enough was the last question about kinetic energy. So it would follow that this sub-question would be about energy. This kinetic energy is going to decrease. It's going to slow down until it reaches its maximum position, at which time all of that kinetic energy will have become spring energy. So our kinetic energy becomes the potential energy of the spring, and the kinetic energy we determined was 0.12 joules, and the potential energy of the spring is 1/2 kx squared. The K we are given on the first page is 100 newtons per meter. So that gives us 0.24 equals 100x squared. And then x squared becomes 0.0024, which seems like it's going to be implausible, but it's not. It's just very small numbers, and the very small numbers occur because we're dealing in meters. And that gives us an x of 0.04895 meters, and rounded to two significant digits, 0.049 meters, like so. So that's how we get the amplitude in that case. The biggest part is connecting the kinematics of this to the energy. Part D asks us to determine the period of the harmonic motion, and this is a horizontal spring, so the period of a spring is given by 2 pi square root of m over k. And this is right off the formula sheet. And so we have 2 pi. The mass is 1.5 and the square root is 100. And that yields a period of the spring of 0.7695 seconds to two significant digits is 0.77 seconds.